share screen. Today Zoom works correctly. Shows me your display. Okay, so welcome back. We are gonna continue discussing Wang-Landau algorithm, isn't it? So that's the subject of today's lecture, Wang-Landau algorithm. And we were discussing, I started discussing this algorithm here. The idea is that instead of walking through the phase space of configurations of a particular model, such as Ising model, we want to go through the phase space of energies. Why? Because the number of energies is way smaller, goes linearly with the number of lattice sites, while the number of configurations goes exponentially with the number of lattice sites. So the idea is that if we move in the space of energies, we're gonna be able to calculate quantities much more precisely for large lattice sites. Now, the algorithm is going to be very similar to the usual Ising model, except that the probability to accept a step is going to be not distributed according to Boltzmann distribution, but according to the ratio of the many-body density of states. Okay, so that's the postulate. Now, what do we do? So we will always accept the move with a smaller density of states, but we often reject the moves that will bring us to the state with a higher density of states. This is just a consequence of this ratio, isn't it? So if the nu is g of E2, if this one, g of E2 is smaller than g of E1, the beginning one, then this is bigger than 1, which means that we are going to always accept the step. While if g of E2 is bigger than g of E1, then this is less than 1, and we're going to accept the step with certain probability, isn't it? So this it just explains this formula here. Okay, then we're going to start with the density of states, which is set to some number such as 1 at the beginning. Then we will try to flip a random spin, and we will accept the move according to this probability. Okay, so we're going to do the same type of local spin updates that we were doing in Ising model. Okay, we're going to select a spin at random, and we're going to try to flip it. However, instead of using the Boltzmann distribution, we're going to use distribution that's written here, so that has to do with the density of states. Now, of course, if we knew what the density of states is, if we had some information, let's say, then clearly we should get well, I explained before, we should get the histogram to be flat, because the probability to visit a configuration is supposed to be, well, has to be proportional to the density of states, but then the probability with which we are going to visit a state is going to be 1 over density of states, because we take this potential probability to be 1 over density of states, so the two should cancel, and histogram should be flat. Now, when we accept the move and visit particular configuration that has this density of states, we would need to increase the density of states a little bit. Why? Because we know that this is the value of the density of states when visited means that should increase, isn't it? We're doing this consistently. So when we visit certain energy, we said, okay, density of states at this energy has to be slightly bigger, because we see that this configuration appears in our random walk. Now, what does it mean slightly bigger? Well, naively, we would say slightly bigger means we're adding +1, because, well, we visit the configuration, isn't it? Therefore, we believe that this particular configuration has one more density of states is bigger for 1, let's say, of the order of 1. I mean, at the end of the day, we will normalize density of states anyway. So any additive factor would be good enough, would be equally good. However, the problem is that if we were changing the density of states by adding particular number, it would take a really enormous amount of time before we get the proper density of states. Now let me explain why. Because it turns out that this density of states is an enormous number. So we know that the two endpoints, so the antiferromagnetic configuration and ferromagnetic configuration has always degeneracy of 2. Okay, so that's kind of obvious, because even if you have very large lattice sites, the ferromagnetic configuration is unique. Up to a factor of 2, basically all the spins can point up or all the spins can point down. So there's always double degeneracy. And there are also only 2 antiferromagnetic configurations. Okay, you can convince yourself that that's always the case. So these 2 endpoints will always be the same. They'll have density of states of 2. However, the density of states in the middle with energy 0, for example, that will grow enormously for large lattice sites. Okay, for 2 by 2 is only 12, but for large lattice sites is enormous. So let me give you an example of 32 by 32 Ising model. So this paper from 1996 calculated exact density of states for 2-dimensional Ising model. So it's exactly the case that we are doing now, 2-dimensional Ising model. And so it turns out that, of course, 2-dimensional Ising model is exactly solvable. So it's not so surprising that that in 1995 this paper found exact density of states. So we have a benchmark with which we can compare our results. And let me give you the number for the density of states for 32 by 32 Ising model. Yeah, so here it is. So the largest coefficients for the 32 and times 32 Ising model is, this is density of states for 512. Basically, it means in our case would be for energy is equal to 0. So this the central point, isn't it? You see, it's this number. Okay, so this integer number. So it's really an enormous integer number, which is roughly 6.3 times 10 to the power of 306. Okay, so imagine that we are jumping through the configurations in such a way that we're adding unity to every time we visit the configuration. So it's going to take an age of the universe to get to this number, 10 to the power of 306, doesn't it? Okay, so adding 1 plus 1 plus 1 plus 1, and before we get to the power of 10 to the power of 306, this will take forever. Okay, so there is no way to jump through configuration and just by adding a number to the density of states. However, the idea is that what if instead of adding a number, we actually multiply the density of states by some number which we call modification number, f. Okay, so we know that if we multiply something with some modification factor which is bigger than 1, then the values will grow exponentially. And somehow our intuition that the values should grow exponentially, well, we get from intuition that these values are exponentially large. In other words, z is exponentially large, and the density of states has to be exponentially large for the many-body system. So we need to do something that will grow exponentially, and this something is basically multiplying the density of states with some multiplication factor f. And we're going to do it in this following way. When we visit particular configuration E, with particular configuration that has energy E, then we increase the density of states by multiplying it by modification factor f. Okay, now what is this f? Well, we're going to select at the beginning that f is equal to 2.718, which is e to the 1. Okay, this is not essential that f is e to the 1. We could easily start with 2, would be okay, because if you multiply something by 2, values grow very quickly, or quickly enough. We could also start with 3, or we could start with 4. It doesn't matter so much as long as we start with some number that makes things grow pretty quickly at the beginning. However, it turns out that if we use this modification factor f to be large, okay, then the density of states will actually not be exact. It's going to be approximate. So we have some systematic error because this f is large, because we are not actually adding 1 when we visit density of states. So if we were adding 1 when we visit density of states, the systematic error would be 0, okay? But we are not adding, we're multiplying. So then, because we're multiplying, that means that we have some systematic error. One can prove that the systematic error is of the order of log f, okay? So of course, if f is 2, then we have systematic error of the order of log 2, which is not exactly 0, so we don't want that. So how do we get rid of the systematic error? Well, we do this self-consistently. So we start with relatively large modification factor, f of 2.7. We run this for some time, and we get decent density of states, which we know has some systematic error, but it's okay as a first approximation, isn't it? And then once we have this density of states, which is a reasonable approximation, then we reduce the modification factor a little bit, and we go closer to 1. So the rule of thumb is to take square root of this modification factor, okay? So the simulation at certain modification factor f is running for so long that the histogram becomes flat. Each energy level is visited equal number of times. Here, equal means that the deviation is within certain bounds, like 80 to 90%. We said before that if our density of states is correct, then histogram should be flat, okay? And that's what we're looking at. So we're trying to see, at the beginning, of course, histogram is not going to be flat because we're basically, most of the configurations have not been visited yet. So therefore, histogram is going to be 0 in many places. But eventually, when we run this for long enough time, we should visit almost every energy, okay? And then we expect that histogram should get flat. And once it gets flat, it means that we have a decent statistics. And then we can say, well, okay, so add this modification factor, which might be 3 at the beginning or 2.7. Statistical error was basically removed. We don't have statistical, well, removed within 10%, let's say. So we have decent statistical precision, but of course we have systematic error because, well, f is still large number. But we have now a good approximation for the density of states. Okay, so therefore in the next iteration, we're going to reduce modification factor so that we're going to take f to be square root of f0 of previous f and run it again. So now in the next step, the density of states will be changed less because modification factor is going to be close to 1. So when modification factor is 1, we are not changing density of states anymore, isn't it? We multiply it by 1. But as long as this modification factor is bigger than 1, we're still changing density of states when we visit particular configuration. So the idea then is that, okay, we reduce the modification factor a little bit. Then we know that we are going to correct the density of states that we obtained before. We're going to correct it a little bit. So the change is going to be slower, but the systematic error is going to be smaller. Okay, so that's what we want. And then once we have slightly better density of states with smaller modification factor, we again reach the point where the histogram is flat, and we repeat the loop. Okay, so the simulation is again running so long that the histogram becomes flat. After that, the histogram is again reset and modification factor is reduced. Okay, so when the modification factor f becomes sufficiently close to unity, the density of states does not change anymore. That's obvious because we are visiting configurations, and the modification factor is essentially 1, which means that you visit a state, you don't do anything with the density of states anymore. Okay, if you are able to obtain a flat histogram using converged G, then the density of states is obviously the true density of states of the model. I mean, that's kind of obvious because we argued, or we explained here, that our probability to accept the step is going to be 1 over our best approximation for the density of states. But we know that the histogram should be flat because, well, we're going to visit configurations we're going to visit those configurations that have large many-body states much more often, obviously, because we're going to do a random walk in energy space. So clearly, if we manage to get the histogram to be flat, then this equation tells you that we have correct many-body density of states. Now, of course, this might be sometimes hard. It might take very, very many Monte Carlo steps. But if we have sufficient number of Monte Carlo steps, we should be able to achieve that goal. Yeah, and basically now here is the example of calculations for specific heat. You see the beautiful curve that diverges, the very, very sharp curve diverges very nicely with the critical exponent. Again, this is 256 by 256 Ising model, so it's still not infinite. Therefore, this curve is still it doesn't go to infinity. It goes to a finite value, but nevertheless, this value is pretty large, so pretty sharp. So we could easily extract the critical exponents. Now we want to code this now. We understand the theory behind it. So let's try to code. It's here, Wang-Landau. So today I uploaded new version of Wang-Landau algorithm, both to our homepage. So if you update your web page, you should see the new version of Wang-Landau algorithm. I hope it's there. And I also uploaded a new version of everything to GitHub. So you can download for GitHub the newest version of Wang-Landau. Now, how different it is? Well, a little bit in the sense that I added the homework. Okay, so when we finish the Wang-Landau algorithm, you will get the homework, which maybe the last, maybe almost the last homework, probably the last, which I think is relatively easy. Basically, I'm going to ask you to estimate the error bar for this density of states. Okay, so we are going to here in this work, we're going to estimate the density of states for the Ising model, and you're going to need to check the error bar on this density of states for 32 by 32 Ising model. Now, why 32 by 32 Ising model? Well, because this paper that I just showed you, this paper from 1995, has published the 32 by 32 case. I mean, here basically he published these density of states. So here is Z, which is e to the some number, which comes from the Boltzmann distribution. But these numbers here are actually density of states. So density of states of the ground state is 2, we said, isn't it? So it can be all spins can point up or all spin can point down. Then it turns out that for 32 by 32 Ising model, the next energy has the degeneracy of 2048. That's actually quite easy to understand. It's actually twice times the 2 to the power of n. Okay, 2 to the power of 32, yeah. So 2048, and then the next energy has this degeneracy and that degeneracy and so on. So you see, you can just read off these degeneracies, and one of the one question in the homework is going to be, let's say that this, well, we know that this is the exact density of states, for the first, this here, they published only first 10 values. They didn't publish all values, and I kind of didn't, yeah, so you see here, this is x to the 20 plus 3 dots, and then this has to be symmetric, so this doesn't contain more new information. It turns out that the rest of the density of states were not mentioned here, except that these numbers are ridiculously large and they're not reasonable to publish. So I didn't go and recalculate them myself, although the algorithm is published here. So if somebody is very good in mathematics, it could try to use Mathematica to estimate more of those coefficients, but I'm not going to ask you this for the homework. I didn't do it, and you don't need to do it. Let's just use the first 10 that are published, the first 10 values, and then from those 10 values, we can check whether how close is our approximate density of states numerically obtained by Wang-Landau and the exact density of states, isn't it? So we can plot the two results, we can estimate our error bar, and we can check whether your sigma square or your estimation for the error bar makes sense, in the sense that your error bar is more or less within the region that your error bar is roughly as large as the error of your as the distance between your approximate density of states and the exact value, doesn't it? But okay, let me return to this when we finish discussing the algorithm. So let's go through the algorithm first. But the important point is you will have a homework from this assignment. Now I should probably restart kernel and clear the output because I had some issues before. Okay, so what do we do at the beginning? So the first cell is just a carbon copy of simulation of the Ising model. So the C energy gives you energy of configuration of any configuration of the lattice of 2D Ising model. So it gives you total energy, doesn't it? We discussed this this last time. Now random L gives you a random configuration for the lattice, which corresponds to the infinite temperature, Boltzmann distribution at infinite temperature. So completely random configuration. So these two should be obvious from the previous lectures. Now this routine, the cell here, is different, is new. So we call it prepare energies. And basically what it does is enumerates all possible energies for the Ising model. We discussed all possible energies for the Ising model. Let me point you to the right place. So all possible configurations for Ising model are those. We discussed that, isn't it? So they start with J is set to 1. Okay, so J is 1. So we have minus 2n is the lowest possible energy, plus 2n is the highest possible energy. And then they vary in steps. Basically, most of the steps are, so 2 times 2 is 4. So most of the steps are 4, isn't it? Those 4. So you see the difference between these two is 4. The difference between these two is 4. But the difference between the ground state and the first exact state is 8. Again, to remind you why this is the case is because when we flip the first spin out of the ground state, we break 1, 2, 3, 4 bonds. We break the most bonds. Okay, so because we break the 4 bonds, the energy cost is 4J, but actually it's twice as much because the spin was down before and then it's up. So basically delta S is 2. So this is delta S is 2 and the number of bonds is 4. So we have the cost is 8. 8J, J is 1, so it's 8. But once you have already one spin that it's opposite, when we flip the second spin, we know that one bond is going to be now antiferromagnetic, and all the rest are ferromagnetic. So the cost is only 2J times 2, which is 4. So this should be now clear that the first jump is bigger, it's twice as big as all other jumps. Okay, so now that you understand which energies are allowed in the Ising model, we should be able to write a simple code that enumerates these energies. So we're going to call the energies, and the energies are. So here is A range. A range, D type is integers. So these A range is a routine from NumPy, which gives you numbers between minimum to maximum in steps of 1, if you don't specify what step is. So I decided to use step 1 actually, and I go from minus n squared over 2 to n squared over 2 plus 1, which basically means all integer numbers between minus n squared over 2 to n squared over 2, because it's less than n squared over 2 plus 1. So again, minus n squared over 2 to n squared over 2. And then I multiply this by 4. So now, if you multiply this by 4 at the end, you clearly see that this is going to go between minus 2n squared to 2n squared in steps of 4. I mean, this could, of course, be done in a different way. I mean, I could, instead of multiplying this A range at the end with 4, I could give step 4 here to the argument of A range, and start with minus 2n squared. I mean, doesn't matter. Yeah, any way would be good, but this definitely contains correct energies. So from minus 2n squared to 2n squared in steps of 4. But one thing that I've done here is I changed, after I got this array, I changed it to list. Yeah, so basically this, if maybe it's better to do it this way. Actually, I didn't think of this before, but we could use range here because we need integers anyway. And we could start with minus 2 n times n, I think, to 2n times n in step of 4. I think this would be actually equivalent. And I think this works. I'm not 100% sure, but I think that this should be equivalent. It may be easier to read. The important point is that this, the final result has to be list. Why? Because from list, it's very easy to take out one or two values. So what we're going to do is once we have the list, we pop out. Pop means take out, okay, remove. So we're going to take out the energy of 1, and we're going to take out the not the last, but the value before the last, doesn't it? So this takes into account the fact that the first energy from the ground state has a bigger gap, not 2 but 4. Not 4 but 8. Sorry, not 4 but 8. So once we take out these two energies, okay, then we create an array back. So before it was array, then we create a list. We pop out the two things that we don't like, and we create array again. So I'm not saying that this is the best way to do it. Probably you can easily improve this algorithm, but the point is that this indeed works. It produces all the energies of the Ising model. Of course, if you want to make this more efficient, what you would do is you would first count how many energies you have, create an empty array, and then populate the array. I think that to write that algorithm to populate the given array is slightly harder to read, but it's more efficient. Now, on the other hand, we don't care about efficiency in this step because we are going to do this only once at the beginning, and we're never going to change it. We don't need to run this many times, so only once. So therefore, the speed is really not important here. So anyway, this produces all the energies of the Ising model. Then the next step is to, well, we're going to check what is the minimum and maximum energy, which of course we know should be minus 2n or minus 2n square or 2n square. But this step is important. So when we visit the configuration, we want to be able to read what is current value of the density of states for this configuration. So let's say that you reach a configuration with energy E, and what we would like to do is we would like to have this density of states at this energy, and we would like to get value of the density of states at this energy. So of course the density of states will be in an array. Actually, we're not going to have density of states, we're going to have logarithm of density of states, because we know that density of states is an enormous thing, so that we need to work with logarithms. But nevertheless, the point is that if you have an energy, you would like to get, you would like to be able to access this density of states very quickly. Okay, so how would you do that? Do you have any idea? So we have energy. We know that. So we know that energy is between minus 2n square to 2n square in steps of 4 roughly. I mean, up to the first and the last energy. And we need to. So these are some integers. So it's not very hard. They're integers, and we need to access an array very quickly. So we use the configuration. We want to very quickly read off what is the density of states of this particular energy. So how do we do that? What would you do? How do you code that? Can somebody help me? Are you alive? Are you thinking? Are you listening? Any idea? Please help me. So I have energies which are integers from, let's say, minus 200 to 200 in steps of 4. And I need to access density of states for that energy, which is some integer. So how do you access this density of states quickly? Any idea? Do you hear me?
We do a quick sort.
Quick sort. Thank you for suggestions. So basically, probably your idea was to use. I mean, these energies are sorted. So what you could do is you could use bisection, for example. So typically, if you have no other idea where the right entry is, you would do bisection. You would say, well, let me try to look if it's in the middle. Then if it's not, is it bigger than this or smaller than that? And then you move your post. Okay, so that's called bisection. But this will be extremely slow. Extremely slow. I mean, way too slow for what we need. So the Pythonic way to do it would be to use a dictionary. Isn't that? You remember the dictionary? Dictionary has an arbitrary type, arbitrary index. Can be even a string. But we could definitely have a dictionary which has indices minus 200, minus 192, 192, 200. Any of those numbers would be fine, doesn't it? So we could definitely have a dictionary where the indices are the energies. Okay, definitely possible, and that would work. Would be much faster than doing search every time. But there are two problems with this. So first, dictionaries are not that fast. They're fast, but they're not that fast. And the second problem is that NUMBA is not going to be very useful once you have dictionaries, because NUMBA is not really working with dictionaries. You know that an equivalent construction in C for dictionary, it's not really existing. So the point is, we need to do something else. So what we do actually is we construct index array. Okay, index array. So what does index array mean? Well, index array means that if you give me an energy, a number E, which is energy, I will give you the index in the array at which the density of states is being stored. Okay, so do you understand what I mean? So this is, basically what we're going to do is, if you get an energy E, then we're going to subtract from this energy E min. So that therefore this E minus E min goes between 0 and some large number. But we know it's finite. And it's not that large, because there are only, the number of energies is only of the order of number of lattice sites. So that's not very large. So E minus E min is a number which goes between 0 to some not too large number. So therefore it's easy to have an array which is called int E that takes this as an argument, and then it will give me just successive number of energy. So for the first energy is give me 0, for the second energy is going to give me 1, for the third energy give me 2, and so on and so forth. Okay, so therefore then I can have a simple array for the density of states that has G of 0, G of 1, G of 2, G of 3, and so on, and I can easily move between them with using this index array. Okay, so that should be that is the most efficient way, kind of obvious. Okay, so let me evaluate this and let me show then what does that really mean. Okay, so look, this is an example for the Ising model with the 10 sites. Okay, let's say we have 10 sites, because I give here input 10. So we are preparing energies. How does the energies look like? So the minimum energy is 200. So the energies are minus 200, minus 192, minus 188, and so on, up to 200. So these are the energies. Now, when we jump from one configuration to another, and we see that the energy is, for example, minus 16, then we would want to know which energy is this in the array. Okay, so clearly if we get energy minus 200, we know that this is the first energy in the array. Okay, so we would then modify the density of states, the first entry in the density of states. If we get energy minus 192, we would like to modify the second entry in the density of states, doesn't it? If we get energy minus 188, we would like to modify the third entry in the density of states, doesn't it? So the question is, how do we do that? Again, we created so-called index array, which is this thing. And you see this index array has lots of numbers which are minus 1. This means that these energies don't exist. Okay, so if we use index array in this way, index E of E minus E min, then when E is equal to E min, we get 0, because this is the first entry. If E minus E min is equal to 1, 2, 3, 4, 5, 6, 7, 8, then we get 1. If E minus E min is equal to 9, 10, 12, 11, 12, if it's 12, we get value 2, and so on and so forth. So if finally the energy is I guess 400, no 200, then we get index 98, which is the biggest density of states. Okay. Now here we did not take into account that the density of states is symmetric, because in general this is not symmetric. But since the density of states is symmetric, we could even make index array in such a way that 0 and basically instead of 98 we would put 0 into index array. Okay, and instead of 97 we could put 1, and in this case we would create only half of the curve. with, and in this case, we would reduce statistical error. But we're not gonna assume that density state is symmetric, because kind of it's not completely obvious at the moment. And we want to see how big, how close to the symmetric curve we're going to get. Okay. So index array. I hope you understand what the index array is. So now, what are we going to do here? We're gonna this small routine will run Wang-Landau algorithm for a particular for a particular size of the lattice sites, linear dimension n, for number of iterations being n ITT, which is going to be maybe 100 million, and then with particular flatness. Flatness means that we are going to require that the histogram is flat up to that number. So typical value for flatness is 0.9, which means that the minimum value in the histogram should be within 0.9 of the average value of the histogram. Okay, so these are the input parameters. And then what this Wang-Landau does is just prepares the energies, basically what we just discussed above. So runs this routine, prepare energy, which gives us all possible energies of the Ising model, index array and minimum energy. So you see, it gives you energies, index array, minimum energy. Then it prepares this random lattice, basically lattice of n by n. Prepares the configuration, isn't it? This is the usual configuration for the Ising model, which is going to be used when we do the when we do the steps of the Monte Carlo. And we're going to select completely random configuration at the beginning. And then we're going to run Wang-Landau with these, with this particular energies, with this particular index array, with this particular lattice. Now, what is this run Wang-Landau? Well, this run Wang-Landau is something that can be optimized with. The reason that I broke these things into two pieces. So something which is called Wang-Landau in run Wang-Landau is because this run Wang-Landau now can be optimized further with Numba. And let's see what this actually does. So this is the heart of the Wang-Landau algorithm. And as you can see, it's not very large, not very long. It's actually pretty small. So it's very similar to the simulation of the Ising model. Very small modification. Let's check what. Okay, so this step is trivial. We just check how big is the lattice site, how big is the dimension of the problem, the size of the lattice. So then we calculate the total energy of the configuration at the beginning, so the initial configuration. Then we didn't remember, let's say, minimum energy, so we kind of update this, or we read off from energies the minimum and maximum energy, and then we set, we initialize the array for the logarithm of density of states. So this LNGE is not density of states, is logarithm of the density of states. Again, the reason that we work with logarithms is because these numbers are very, very large. So we cannot work with density of states directly. We would get overflow very, very quickly because, as I demonstrated before, the density of states for a 32 by 32 Ising model is of the order of 300. And moreover, this density of states that we work with is not normalized. So we were going to very, very quickly blow out of the the values that are allowed for double precision. So we want to work with logarithm of density of states. Now the histogram, on the other hand, is we don't need to use logarithms. So histogram is just you're going to see how often do we visit energies, different energies. So both histogram and logarithm of density of states is of the size of array energies. So as many energies as we have, so many density of states entries we need to have, isn't it? Because density of states is associated with energy, isn't it? So it's G of E. So density of states at particular energy. We're interested in density of states at particular energy. So therefore, this has the size of energy. The same for histogram. So this shows you that we are actually visiting configurations. We are walking through density of states that have different. We are walking through the configurations that have different energy. Now, this LNF is modification factor, which is this quantity that we multiply density of states with, but actually we are not going to use directly modification factor F. We're going to use logarithm of that modification factor. Again, why? Because we are working with logarithms. So logarithm of density of states, logarithm of modification factor. So at the beginning, modification factor is set to 2.7 something, which is e to the 1. So therefore, logarithm of the modification factor is actually 1. What I want to say is that we are setting this modification factor f to be e to the 1, which means that logarithm of the modification factor is actually 1 at the beginning, isn't it? So logarithm of modification factor is 1. Then n2 is n times n is number of lattice sites. So then we have this very, very large loop over many, many million steps, isn't it? Maybe 100 million, which hopefully is optimized by the NUMBA well. And so what do we do at each step? Well, this part is actually exactly the same as the Ising model simulation. So we randomly select lattice site. We look at its index ij, and then we look at the spin at this random site. Okay, we look at the spin. What is the spin? We look at what is the Weiss field at that site, which again is you look at the left neighbor, right neighbor, upper neighbor, lower neighbor, and then we calculate what cost of the energy is associated with single spin flip at that site. So how much energy do we need to pay or gain when we flip the spin? And again, this is exactly the same as in the Ising model simulation. So we calculated that the change of the energy is 2 times spin times the Weiss field. Now here I use typecasting to integer. Now I'm not exactly sure if that's actually needed because I think the spin is integer, Weiss field is integer. So I think that this actually is integer is not even needed. But the point is that we do want energies to be integers. So I guess maybe in Python 2 or something, I didn't have something wasn't integer. I don't know whether S or VF, but I think that here lattice is probably integer, so which means that S is integer, Weiss field is integer. So basically, this integer is probably not essential here. Anyway, so this is the new energy or the energy associated with single spin flip. Okay, so in the Ising model, what we said is that we are gonna see in the Ising model was the same. So Weiss field, and then we said the energy cost is e to the minus energy divided by t. Okay, and then we pre-computed the exponents, and we calculated the energy cost associated with Boltzmann distribution. But in this Wang-Landau algorithm, we actually jump with the probability which has to do with the ratio of the density of states. So we want to accept the step with probability that is density of states of the old with the old energy divided by the density of states of the new energy. Okay, so let me remind you where this comes from again. So in this derivation that we've done before, we said that we're going to take probability to be ratio of the old divided by the new density of states, or whichever is smaller. So that's what this is supposed to do. G of V divided by G in U. So, however, we are not using density states, we are using logarithm of density states. Therefore, we can calculate that by exponent to the logarithm of the density states minus logarithm of g of the new density states. So you see, we can take the exponent and then we have the difference of the logarithms. Okay, that's kind of obvious. Now, the quantity in lnge is actually logarithm of density states. So basically, what we need to do is we need to take logarithm of density states of this old energy minus logarithm of density states of the new energy, and then we take the exponent of that. Now, of course, we spent a lot of time before to figure out that in order to access the density states, we need to use this index array. Okay, so now you understand why this index array was important. So what we do is we got the new energy in U, and we subtract from it minimum energy because we want this number to start with 0 and go to some large number, and then we take index array of that number, and this number is going to be between 0 and the number of energies that we have, isn't it? This will go in the correct limit from 0 to the number of energies and will correspond to the entry in the energy. So now this gives you correct logarithm of density of states for the new energy, and if we put in here n instead of a new, we get density of states of the previous or current, we can call it current density of states for the current energy. Okay, so now we have the logarithm ratios, and then we calculate probability to be exponent to this Lg out minus Lg new, because we said that probability has to be exponent of the difference in the logarithms. So now it turns out that calculating the exponents itself, exponent is actually not that cheap. So you need around 50 or so clock ticks to calculate an exponent. So therefore, we are not going to calculate it every time. If we know that exponent is bigger than 1, then there is no point of calculating it. So why would you want to calculate exponent to the positive number if we're never going to need that, isn't it? Because if this Lg alt minus Lg new is bigger than 0, then exponent is bigger than 1, which means that we will definitely accept the step. Okay, so therefore we set p to 1 at the beginning. We could set it to 2 or 3, or it doesn't matter, some number that's bigger than 1, and then we calculate this p. We modify this p only if we know that p is less than 1. And then the probability should be this exponent. And then we said, okay, if this p, if we then we accept the step with this probability, isn't it? In so following way, we draw a random number between 0 and 1, and we accept the step if our probability is bigger than that random number. Okay, so that's the same as an Ising model. The only difference is that p right now is computed by this ratio of the density of states. That's it. Okay, so otherwise we're doing the same. This is typical Metropolis algorithm. So now, if the step is to be accepted, then we modify the value of this spin on the side, and we change the energy, because the energy has to be updated when we flip the spin. Okay, so basically, compared to the Ising model, the only modification is, as I said, is this few lines, which basically changes acceptance step probability. Acceptance step probability is not Boltzmann, but it's proportional to 1 over the current density of states. Okay, of course, we don't know the density of states yet. We need to do this consistently, but at least if the logarithm density of states is correct, then we are accepting these steps with the ratio of the the G old divided by G new. Now, in order to know whether statistical error is small, is to look at the histogram. So we said that if statistical error for density of states is being relatively small, then we know that the histogram is supposed to be flat. Okay, so at the beginning, when we visited almost no configurations yet, the histogram is going to be awfully non-flat. But if we run this for several million steps, and therefore we're going to visit every energy maybe 100,000 times, then we know that the histogram will eventually get flat. Okay, and when the histogram is flat, we're going to reset the whole thing. Okay, now, but in order to do that, we need to first create a histogram. So at the beginning, histogram was set to 0. And then every time we visit the configuration, we're going to increase the histogram for 1. That's what histogram is. So it counts how many times did we visit particular energy. That's the histogram, isn't it? If we visit it again, we're going to change we're going to change the histogram again. Now, density of states, however, is different. So we said that the density of states is going to be changed by modification factor, and in such a way that the density of states is going to be multiplied. So here we said the density of states is going to be multiplied by modification factor f, which means that the logarithm of the density of states is supposed to be added logarithm of f, isn't it? So the idea is that g of e becomes g of e times f, which means that logarithm of g of e becomes previous logarithm of g of e plus logarithm of f. That's kind of obvious. Again, the rule of how we treat products in logarithms, products in logarithm. So therefore, we are adding to logarithm of density of states this ln f, logarithm of modification factor. Yeah, so we are running this for some time, let's say 1,000 iterations, and then every now and then, which is in this case 1,000, I hard coded 1,000 steps. Maybe 10,000 is equally good. Just don't do this too often because it's kind of expensive. So then every now and then, what do? Well, we check how flat is the histogram. So what does it mean? Well, we calculate the average value in the histogram. Average value is sum of all entries in the histogram divided by the number of number of lattice sites, and then minimum value of the histogram is, of course, just well, we can use min of histogram from SciPy, and then we say if the minimum value of the histogram is bigger than the average value of the histogram than some number, which is in this case 0.9, then we can say histogram is flat. Okay, why? Because, well, when histogram is flat enough, minimum and the average value should be pretty close. Okay, that's all there is to it. Yeah. So once we realize that the histogram is flat, we will reset the measurements. So we're going to set histogram to 0. We're going to reduce the modification factor per factor of 2. Now this means that logarithm of the modification factor is going to be reduced by 2, which is equivalent to saying that modification factor is going to become square root of the previous modification factor. So you see, if modification factor becomes square root of the previous modification factor, means that the logarithm of f is going to be logarithm of previous f divided by 2. again, because of the laws of logarithms. So, and then we also print out something about the current configuration, that the histogram is becoming flat, and that's it. So once we make the histogram flat, we go back and we improve a little, we run again our simulation and improve the density of states. Okay, so is this algorithm clear? Anybody? It's clear? Not clear? Too obvious? Clear. Okay, great. At least clear to some of you. Okay, so let me evaluate this. And now, yeah, so from NumPy import random, so we need to import this random. If you don't do that, it's going to be an error. Then we're going to set flatness to 0.9, which means that we want a pretty flat histogram. Then we're going to take the lattice site size to be 20 by 20. We're going to take 100 million iterations. Turns out that we need quite some substantial number of iterations so that the histogram can become flat many, many times, and modification factor should become pretty close to 1. So with 10 million iterations, unfortunately, we're not going to get far. And then we run this Wang-Landau that we just explained. Okay, so let's do that. Whoops, Wang-Landau is not defined, which means that I did not, I didn't evaluate this thing, and this thing, and then this thing. Okay, so it's running. And you see, we needed something like 1, 2, 3, 4, 5, 6. We needed 10 million iterations to get histogram flat with a modification factor 1.6 or something like that. So we need quite large number of iterations. So eventually, with 100 million iterations, we were able to get modification factor down to 1, 2, 3, 4, 5, 10 to the minus 5, close to, or 6, 1, 2, 3, 4, yeah, 5, 1, 2, 3, 4, 5, 10 to the minus 5, close to 1. So this is pretty small modification factor. When modification factor is that small, then we can be pretty certain that, and the histogram is flat, we can be pretty certain that density of states make sense. So now the issue is, however, then density of states right now of logarithm of density of states of the first ground state and of the last state is some number, 28,260. Okay, so what is supposed to be logarithm of density of states of the ground state? Anybody? What are we expecting for this number, logarithm of the density of states of the ground state? Can you tell me? Well, I was trying to explain that the ground state is doubly degenerate, and that it remains doubly degenerate even for large systems. So this one's doubly degenerate, and the most excited state is doubly degenerate. So if that's true, then the logarithm of density of states is supposed to be log 2. So this number here is supposed to be log 2, and this number here is supposed to be log 2. Okay. So why it's not log 2? Well, because this condition that a histogram is flat, it just gives you density of states up to a constant. So the entire density of states curve is correct, but it's not properly normalized. Okay, why? Because when we visit configuration, we either add some number or we multiply with some number. But of course, the longer we run, bigger these numbers are going to be. Okay, so when we run this more, we're going to get bigger numbers. The curve will definitely look correct, but the normalization is going to be wrong. Now, is this a problem if normalization is wrong? Well, not really, because we can always normalize the density of states at the end with the proper normalization factor. So how do we do that? Well, the important thing at the beginning, the important thing to point out is that this logarithm of density of states is symmetric. So within statistical error, of course. So we see that this number both numbers are of the order of 28,260 and something. So this is pretty close to symmetric. This is good. So all we need to make sure is that we multiply this logarithm of density of states we need to multiply density of states with a number which will make this value as log 2. So if we want to multiply the density of states with particular number, that means logarithm of density of states needs to be just added. So we need to just shift, add the number, shift the entire curve by correct value. So what would that value be? Well, it's actually easy. So if we look at the G density of states of the ground state and density of states of the most excited state, ferromagnetic and non-differential configuration, then G of 0 should be 2, G of -1 should be 2, and the two together should be 4. So if we multiply the current density of states with 4 divided by G of 0 plus G of -1, we clearly will get correct normalization for density of states. Is this clear? So we know that G of 0 and G of -1 are not correct. They're not 2 and they're not 2, but they're supposed to be 2. Okay, so G of 0 is supposed to be 2, G of - is supposed to be 2. We cannot force both of them to be 2. Why? Because, well, they're not exactly the same. They're similar, but they're not exactly the same. So the best you can do is to take both of them together, you add them together, G of 0 and G of -1, and you require that those two are equal to 4, that the sum of the two is equal to 4, isn't it? Because G of 0 should be 2, G of -1 should be 2, but again, due to statistical error, these two numbers are not going to be exactly the same. So therefore, the best you can do is we can say that the sum of the two should be 4. So if you multiply the density of states, current density of states, by 4 divided by the sum, G0 plus G -1, we see that this will properly normalize density of states. Okay, so now if this is clear to you, then the rest is completely simple math. So now you do not want to get overflow. The problem is that these numbers, logarithm G of V is enormous number, is 28,000. These are all logarithms. So what you're supposed to do is supposed to calculate exponents of that, exponent of 228,000, okay, to get G. So this is way too large number to think about, okay? So there is definitely going to be overflow. So therefore, this already shows you that you're not supposed to work with density states. Okay, you're supposed to work with logarithms only. So in order to avoid evaluating ever G0 or G -1, we're going to work out how do we work with logarithms. So we can write this as 4 divided by G of -1 times 1 plus G0 divided by G of -1. So you see this expression here is exactly equivalent to the previous expression. So these two expressions are exactly 1-to-1. Okay, except that I have here a nice ratio, G of 0 divided by G of -1. So the ratio of these two, we know that G of 0 and G of -1 are almost the same. You see, this is very, very close to 1. So when we take the ratio, we get a number which is very, very close to 1. That's not hard to handle. So whatever is here in the brackets, it's very easy to handle. Now this 4 divided by G -1, these are very, very, very large numbers. But we don't need to ever evaluate them because we're interested in logarithm of G, not G, but logarithm of G. So logarithm of G has to be what? So now I'm taking logarithm of this equation on the left and on the right. Okay, we're taking logarithm of that equation. So what is logarithm of that equation? Well, on the left-hand side, I'm getting logarithm of G plus equal. So times equal becomes plus equal, isn't it? It's obvious, isn't it? So let me write one more step. So what we're supposed to do is we're supposed to get this G is equal to G times, or we could say that G is equal to G plus 4 divided by G minus 1, 1 plus G0 and 1. Okay, so which means that logarithm of G, so I'm taking now logarithm on both sides, is equal to logarithm of G plus logarithm of 4 minus logarithm of G of minus 1, is that, minus logarithm of 1 plus G of 0 divided by G of minus 1. Okay, so I'm just using the usual properties of logarithms. Okay, very simple. Okay, which of course means that logarithm of G should be added plus equal this quantity, isn't it? Which is logarithm of 4 minus logarithm of G of minus 1 minus logarithm of 1 plus this thing. Now what is we are not storing G of 0, we're not storing G of 1, we are storing actually logarithms of that. So therefore we need to write it as exponent of logarithm of G of 0 minus the difference of logarithms. Okay, so these are only, this last line contains the quantities that we actually have in our calculation. Okay, so therefore what we're going to do is we're going to calculate now this quantity. Okay, so we're going to calculate this, which we are going to call log C, LNC. LNC, LGC actually. LGC is this quantity. So what is it? Well, is logarithm of 4, clearly that's logarithm of 4, minus ln e minus 1, which is logarithm of G of minus 1, and then minus logarithm of 1 plus exponent to the logarithm of exponent to the of logarithm of G of 0 is ln G of E0 minus ln G of E minus 1. Now, yeah, basically, there are two ways to do that. I mean, I think if we just use only this way of calculating, it will work. But if the statistical error is very large and these two numbers are kind of very different, then it's safe to take out. It's safe to take out here not just G of minus 1, but we could also subtract out G of 0 depending on which number is bigger. That's not so important because these numbers are more or less the same. So basically, just calculating log GC always in this way, it's probably going to work. It's not going to have an overflow. But the important point is that this number, LGC, you see, is now all the terms here in this calculations are of the order of 1. They're not a problem to calculate. So log 4 is of the order of 1. ln G E of minus 1 is some number, clearly floating point number, whatever we have in our configuration. And then this logarithm here is also of some reasonable numbers. So these two are more or less the same. So the difference is going to be close to 0. And then we do exponent of something that's close to 0, which is going to be close to 1. So therefore, this here in logarithm, we're going to have a number which is of the order of 2. So in other words, all the quantities that we enter in this equation at the end of the day are nice. There is no overflow. But if we literally implement this quantity here on the top, we're going to definitely get an overflow. So we should not avoid overflow. Okay, so then once we get this LGC, all we need to do is to modify the current logarithm of energies with this constant LGC. We're shifting it properly. Okay, so now I hope I explained to you how we do that. And now you see that if we now check what is exponent of logarithm of E0 plus exponent logarithm of E1, which is G0 plus G of minus 1, is equal to 4. That's what we wanted. We can also plot, we can also print what is actually exponent of ln Ge of 0 and exponent of ln Ge of minus 1. And they're supposed to be 2. So again, because of the statistical error, they're not exactly 2. One is 2.00 something, and the other one is 1.99 something. But the point is they are close enough to 2. And that's what we wanted. So the ground state and the ferromagnetic and non-ferromagnetic configurations, we know that they're doubly degenerate. And now the curve of the density of states is properly normalized such that reaches 2 at the endpoint. And now we are plotting here the entire curve, logarithm density states. So we have 400 entries. Yeah, so we know that this first value here is 2. The last value is 2. But in the center, it goes up to 250 and more. Okay, so relatively large number. Now, of course, this is logarithm. Okay, so therefore, the density of states goes to the exponent to the power of 250. And when the lattice size is bigger, not just 20 but 32 maybe, then this number is going to be even bigger, isn't it? 350 or something. So definitely we're getting overflows all the time. Okay, but now that we have density of states, now we have simple problem to do. We just need to calculate thermodynamics from this. We can calculate all the thermodynamics. So how do we calculate thermodynamics? Well, this is easy. Well, we can calculate Z. We can calculate the average energy. We can calculate specific heat or anything, because so did we discuss this? Yeah, because we know that the free energy is just this. Okay, so free energy is minus cosine t logarithm of g of e minus e over t. So from this, of course, you can get any thermodynamic quantity you want. You can calculate, of course, the simplest one, of course, is the average energy. So the average energy is basically just the energy times the density of states divided by Z times e to the minus e over t. We can calculate average energy square. So then this A of E is going to be E squared, G of E divided by Z, e to the minus e over t. Okay. So, and specific heat finally is going to be, of course, we discussed this last time. Specific heat is given by E square, is given by this E square minus E average square divided by T square. Okay, so if we calculate E average E square, then we can calculate also specific heat. So how do we do that? Well, simply once we have density of states, then we just go over all energies and we sum up proper Boltzmann, we add proper Boltzmann factor. This is it. So we have to do actually exponent of logarithm of density of states, because this is real density of states. Real density of states is exponent of the logarithm of density of states, doesn't it? So this is density of states times e to the minus. So basically Z. So what I'm trying to say is that Z we should add exponent of logarithm of density of states G, doesn't it? Times e to the minus energies e to the e basically, or energies of I. E is actually energy of Y, doesn't it? E is energy of Y because we go through enumerate. E divided by T. Okay, this is it. It's so simple as that. Z is just this. Okay. Now again, there is an overflow problem which I need to explain. So we are not gonna use Z itself. We're gonna use something which we call W, and this W is actually Z divided by Z0 is W. Okay, so basically Z0 is equal to exponent of logarithm of G of 0. Well, this is actually G of 0. So this is going to be G of 0 of the ground state times exponent of minus energies of 0 divided by T. Okay, so we're gonna, in order not to get overflows again, because even energies of 0 is a very large number. So we could get an overflow. We're gonna then divide Z by certain constant, and that's okay because we are gonna this energy, average energy, the numerator will have this quantity, and the denominator will have this quantity, and they will cancel. Okay, so you can always divide numerator and denominator with this number. So then average energy is just this weight, which is kind of z times energy, and energy square is just this weight times energy square. As simple as that. And then at the end, we need to divide all the thermodynamic quantities by z, of course. And again, when we divide by this annoying z0 that we used is cancelled out. And then specific heat is E squared minus E average squared over T squared. So very easy thermodynamics. I'm going to discuss this next time a little bit more precisely. But yeah, you see, there is some runtime overflow problem, because at the end of the day, we will never use z, but if we wanted to calculate z here, and this z is just too big number, so it complains. And then finally, we plot the total energy and the specific heat, and we see specific heat now has a nice maximum here. Of course, the lattice size is still not so big, so this number is not that large. But for the homework, we're going to do 32 by 32, and that's much larger. So therefore, this peak is going to go much higher. Yeah, this is more than enough for today. So is there any question? Any question, anybody? No questions? So then let me